Hello and welcome. I'm Bob Berry and I'm here with my partner Jason Hernandez. Say hi, Jason.
Hello.
That's Jason, and today we're going to demonstrate our ECE120 Lab Final Project. What we have designed is an assembly language port of the classic whack-a-mole game. You know, the game where moles pop randomly out of a hole and you've got to whack them with a hammer for points. In our design, however, the moles have been replaced by LEDs, and instead of whacking them with a hammer, which would make for a very short game, you've got to press a push button that corresponds to a mole that is currently out of its hole, or an LED that is lit up. To win the game, the player must successfully pass through 5 levels of increasing difficulty by whacking at least 5 moles. If he attempts to whack a mole but misses, he is brought back a level, given that he is not already on level 1. Once the game is won, all the LEDs stay lit up until the board is reset. The system is notified of an attempted hit by the player via the RBIE interrupt, which calls the interrupt service routine anytime a change of state is detected on port B between ports RB4 and RB7. Because the push buttons are wired to ports 4, 5, and 6, the RBI flag is thrown and the interrupt is called anytime the player attempts to whack a mole. Once inside the ISR, the program compares the user's input to the current mole configuration to determine whether or not the user has made a successful hit. The player is kept on their toes by the utilization of a pseudo-random pattern-generating routine, in which the current configuration of the moles is determined by a pseudo-random process. Pseudo-random being defined as of, relating to, or being random numbers generated by a definite, non-random computational process. That's from thefreedictionary.com. This makes LED patterns appear to be randomly ordered and allows for varied gameplay and increased difficulty. As we mentioned in the overview, the player must successfully advance through 5 levels to win the game. The first level has the highest delay time, meaning that the moles stay out of their holes for the longest amount of time, making them easy to hit. When the user presses a push button that corresponds to a mole that is currently out of his hole, he advances a level and the moles speed up. When he presses a push button that does not correspond to a mole that's currently out of its hole, he is decremented a level and the moles slow down, making them easier to hit. If he's already at the first level, he will remain there. When the player progresses a level, the LEDs display a pattern moving upward, signifying his progress to the next level. When the player is decremented a level, the LEDs display a pattern that moves downward, signifying that he has lost a level. The next few slides will illustrate some basic gameplay. Win condition?
Yeah, go ahead.
Okay. Oh. Start. Oh, got it.
There we go.
Shown is the initialization section of the program's code. General.h is included to define the location of standard registers such as the status and option registers, and the configuration bits are set with the watchdog timer turned off. T-delay holds the number of delay loops that will be executed during delays within the current level, which manages the speeding up and slowing down of moles. Offset holds the current index for the table of patterns, which determines which moles will be out of their holes. Order stores a value that determines how the current pattern will be presented. Pat contains the current pattern, or mole configuration. Level stores the value of the current level. WTemp and statusTemp store the contents of the W register and status register during the interrupt service routine. Temp1, Temp2, and Count all store countdown values that are used to determine the length of delay routines. T-level temporarily stores the value of level during an algebraic routine that determines delay time. Pat temp temporarily stores the current pattern for manipulation, and temp3 is used to store user input and compare it to the LEDs. Now, in the start loop, the program first configures port A and port B, setting all of port A's bits as outputs and 3 of port B's bits to inputs, the 3 corresponding ports being connected to the 3 push buttons. Then, an initial pattern is displayed which consists of the 3 LEDs flashing on and off twice. The program then goes to the initial loop. Once inside the initial loop, the program first clears the contents of port B and then moves the current contents, which contain the player's push button information, into the W register. The push button bits are then masked to isolate their values, and the 0 flag is checked to see whether or not any buttons were pressed. If the flag is clear, which indicates that the user has pressed a button, the program moves on to the next loop. If there is no input, the program increments the value of offset, and then uses an XOR operation to determine whether the value of offset has already reached 37, in which case it is brought back to 0. The value of offset will later be used to determine the starting location within the mole configuration pattern table. In this way, the starting configuration of the moles is determined pseudo-randomly by rapidly incrementing the offset variable while waiting for the player to start the game. Note that offset is cycled back to 0 upon reaching 37, because 37 is the number of patterns within the pattern table. Now, inside the next loop, the program first configures the int_con register, enabling the global interrupt enable bit and the port B change of state interrupt enable bit. Then, a pattern is retrieved from the pattern table based on the current value of offset, which, as we discussed, has been determined pseudo-randomly while waiting for the player to start the game. A pattern is returned and moved into the pat register. Next, the first 2 bits of pattern are masked using an AND operation, and this value is stored in the order register. The value of the order register will later be used to determine how the pattern is displayed. For now, offset is incremented and cycled back to 0 if it has reached 37, to ensure it does not exceed the maximum number of patterns. The following slides will demonstrate the use of the order register, which is used to add another level of complexity and apparent randomness to the appearance of the moles. Being a 2-bit value, order can only be one of 4 possible values. The check loop checks for these 4 conditions, and based on the current condition calls a corresponding pattern display scheme. This first condition, which is the 0, condition, calls the normal LED scheme, followed by a delay. Once again, offset is checked and limited to its maximum value of 37. Next, the program checks order for the 0, condition. This check is run twice, and if the value of order is 0, the program will first call the normal LED lighting scheme, and then the inverted lighting scheme. During both checks, the program will increment offset and ensure that it is limited to its maximum value of 37. The 1, condition is very similar to the 0, condition, but the inverted LED routine is called first, and then the normal routine. Finally, the 1, condition is very similar to the 0, condition, except that it calls the inverted routine instead of the normal routine. As with all of these sequences, offset is incremented and ensured limited to 37. This is the code for the normal LED pattern presentation, or mole configuration, which positions moles according to the order that they appear within a pattern. First, the carry bit is cleared, and the current pattern is stored into pat temp. Pat temp is then rotated through the carry bit 4 times, and the result is sent out to port A, which lights the LEDs. This has the effect of isolating the top 3 bits of the original pattern. LED delay is called after the pattern is sent, giving the player a moment to hit the moles. Note that the length of LED delay is contingent on the current level, which is our means of scaling difficulty. The LEDs are then cleared, and the original pattern is moved back into pat temp. The pattern is then shifted right twice to isolate the first 3-bit pattern and send that result to the LEDs. This will make more sense if you recall that the first 2 bits of any pattern determine how the pattern is displayed, which is why we first shift the pattern to the right, allowing us to discard those bits and isolate the first 3-bit pattern. The inverted mole configuration routine is very similar to the normal routine, except that the first 3-bit pattern is isolated and sent to the LEDs first, and then the second. Also, the complement F command is used to invert the bits before sending them to port A. This is our pattern table, which contains all the possible patterns that can be presented. Recall that the first 2 bits of these 8-bit patterns are used to determine the pattern's method of presentation, being either normal, inverted, or a combination of the two. The other 6 bits contain 2 3-bit patterns which are used to determine the placement of the moles. The LED delay loop contains the variable delay routine that is used to modulate the difficulty based on the player's level. First, an initial maximum value is moved into T-delay, and the value of the current level is moved into T-level. Inside D-start, 10 loops per level is subtracted from the main loop count, which has the result of shortening the length of the delay, and making the moles appear and disappear faster. This is accomplished by decrementing the temporary value of level within every loop until it reaches 0, and performing the subtraction for every non-zero result. Once we perform a number of iterations equal to the current value of level, we move on to the main delay routine. Shown is the code for our 2 delay routines, one of which is static and the other being dynamic and based on the current value of T-delay. This code exploits the length of the PIC16F84A's clock cycle by performing a large decrementation within 3 loops, causing a delay as the system works to perform the computation. Finally, once the player has won, the system remains forever inside winner loop, in which port A is used to permanently light up all the LEDs. At this point, the game can be restarted by resetting the PIC trainer board.